Time travel, one of mankind's favorite fantasies. But what if it were possible to build a real time machine and travel to the future or the past?
The invention of a real-time machine would probably be the most important thing in the history of the world, in the history of man.
Scientists are now teetering on the edge of making the impossible a reality.
This century, I feel, will be seen as the century of time travel, just as the 20th century was seen as the century of space travel.
Here in this laboratory, the first real attempts to travel through time will soon begin. The future and the past may never be the same again. Imagine a time, say about 100 years from now, when time travel is no longer science fiction. Instead, it's taught to our great-great-great-grandchildren as science fact.
Okay, listen guys. We've got a lot to get through today, okay? Shh. So keep close together. No wandering off. Now come with me.
Here stands a monument to mankind's greatest single scientific achievement, a museum of time travel. Such a museum would be a popular attraction, an edifice designed to tell a story that for us has yet to happen. Strange as it may seem, this future is not beyond the realms of possibility, for we are on the threshold of mastering time itself.
So here it is, the Museum of Time Travel.
So this museum was built on the site of the very first successful time machine. And we're going to find out later why that makes it so very special. But for now, the first step on our journey is to have a look at the past.
Imagine what it was like over a century ago, in an age where the future was uncertain and the past a bit of a mystery.
The history of time travel begins with fantasy and fiction, the compelling dream of visiting another time. Imagine, for example, traveling back to April 1912 and averting the catastrophic loss of thousands of lives by warning the captain of the Titanic of the iceberg. Or how about visiting Germany in 1938 and assassinating Hitler, thus preventing World War II? Tinkering with history is easy to imagine, but in reality, even the basic concept of time is a tough one to grasp.
Time is the weirdest thing. You cannot see it. You cannot touch it. You cannot smell it. And yet it rules our lives with absolute control. We are all carried along in the present. We're trapped in this moment that we call now. Or at least we were, until the efforts of these great minds freed us from the tyranny of time.
In 1905, Albert Einstein came up with a theory that allowed scientists to take over where the dreamers had left off.
Most thought that time travel would never be possible for real. But way back in the early 21st century, one man has an idea. His name is Ronald L. Mallet.
One day, Ron Mallet may be seen as a true pioneer. He believes he's very close to the ultimate prize, a real, working time machine. It is the culmination of a lifelong quest that began with the death of his father.
The reason I became interested in time travel was my father. He was really a terrific person, and I loved him very deeply, and he died of a heart attack when he was only 33, and I was 10 years old, and I was devastated. It turned my world upside down.
Science fiction became the young boy's salvation, for in it, he found the hope that he needed to overcome his grief.
I thought, what if I could build a time machine and go back into the past? Then I would be able to see him again and maybe save his life. So that became my goal, to build a time machine.
As Ron grew up, he began to study science as well as science fiction, discovering a natural talent for the subject. Fast forward 40 years, and the young boy with the impossible dream is now a professor of physics at the University of Connecticut, an expert in the one branch of science that allows him to tinker with time. The journey has certainly been worthwhile, for the fruits of his labors are tantalizingly close.
I feel that with current technology, it's possible at the very least to send subatomic particles back into the past.
The professor's confidence is well-founded. This is a recently published paper in which the principle is outlined. It's been received enthusiastically.
We've known for a long time that time travel is possible in theory. What we've never known is how to do it. But what Millet has come up with here is a means to achieve it. He's got a blueprint for a time machine.
Physicist and writer Dr. Michael Brooks is well aware that sending particles back in time would also allow information to take the same route, and then things would get really strange.
The implications of time travel are truly amazing. If we could send information back from the future, then we could win the lottery, for example, every week. We could manipulate the stock market if we wanted to. But what's really astounding is that we could send back scientific understanding from the future. That hardly bears thinking about.
This paper could revolutionize the world we know, shattering forever the barriers between the past, the present, and the future. Although the professor's idea is new, the underlying science is very well established. In fact, the first steps towards it were taken a long time ago.
Now, this next exhibit features Simon Wells, who's the great-grandson of the man many call the original father of time travel.
Hi, my name's Simon Wells. My great-grandfather was H.G. Wells. In 1895, he wrote a very famous book called The Time Machine. And early in the 21st century, I made a movie out of that book. Do you want to take a look?
The Time Machine was not only a good book, it also set the precedent in which fiction inspires reality. It's the story of a Victorian scientist who tries to go back to prevent the murder of his fiancée. The sad bit is that he discovers he can do nothing to change the past, and eventually he travels into the far future to witness what becomes of the human race. When it was published, The Time Machine immediately seized the public imagination. But the amazing thing is, it was also responsible for the first breakthrough in the real science of time travel.
The breakthrough was to treat time as a fourth dimension, a dimension in which it may be possible to travel.
Just like traveling across a city. Imagine Professor Millet gets an invitation to a meeting in New York City. Thanks. To make sure he gets to the meeting, the invitation must have a number of pieces of information on it. First, he needs a street number. Since New York is laid out on a grid, that number will give him a position in the north-south direction. Next, he needs the avenue. In this case, Fifth Avenue, which gives him a position in the east-west direction. So far, he has found the unique location of the meeting in 2 directions, or dimensions. Now he needs another piece of information to tell him where the meeting is in the 3rd dimension. But of course, the position in 3 dimensions is not enough to make sure he gets to the meeting. The invitation must also carry a 4th piece of information: the time. 4 pieces of information specifying a single event in 4 dimensions, 3 of space and 1 of time. So here is a single event in space and time, or as scientists call it, space-time.
Treating time as a dimension means that scientists can not only consider time travel logically, they can also explain why it seems so utterly confusing to us.
Suppose that there is a world that has only 2 dimensions, like this piece of paper, and that there are beings that can only live in this 2-dimensional world. They can conceive of length and width, but they cannot conceive of the 3rd dimension, height. What would they make of a 3-dimensional object, like this paperclip, if I introduced it into their world? To them, it will appear as though the object came out of nowhere. They can't conceive of the fact that it came from a 3rd dimension. And if I pull the object back out of their 2-dimensional world into the 3rd dimension, to them it will have appeared to vanish.
In just the same way as a creature from a flat world would see a 3-dimensional object doing the impossible, we humans, being 3-dimensional, would see a traveler in the 4th dimension do some very strange things too. Like the paperclip, a time traveler would simply vanish, to reappear in another time.
And that's not the only strange thing that happens. If I fold this piece of paper over and push this single paperclip through, the people in this world will see this one object in 2 places.
Thanks.
That's why time travel, which is travel in the 4th dimension, allows someone to be in 2 places at once.
If a professor could travel back in time, he could be the one who gave himself the invitation to the meeting. It sounds strange to us, but that's because we're not used to seeing travel in higher dimensions.
This sort of thing was the very reason why time travel was thought to be impossible. But as we know, it's not. And in fact, as early as the 1970s, people have been traveling in time just by getting on board a primitive chemical rocket.
Not many people realize it, but time travel has already been achieved, although not in quite the way that Hollywood would have it.
This is what makes time travel possible. The flux capacitor.
Flux capacitor?
In the movies, time travel is usually invented by a crazy professor who builds an even crazier machine. But in reality, there is already a way to take a shortcut to the future. All you need to do is travel very, very fast and for as long as possible. For example, if you were part of the Russian space program of the late 20th century, you would already be one of the world's first time travelers. This is cosmonaut Sergei Avdeyev. He holds the record for spaceflight, having spent a total of more than 2 years on board the Russian space station Mir, orbiting at 16,000 miles per hour. Spending so long going so fast means that Avdeyev is also the current world record holder for time travel. He has been propelled a fraction of a second into the future.
Most people think that time passes at a steady rate, no matter where you are or what you're doing. So a minute in New York is the same length as a minute in London, or Paris, or Tokyo, or the moon for that matter.
It's perfectly natural to think of time as being fixed, as if there could be a giant master clock for the whole universe, allowing us, or any other civilization, to agree on the one true time forever and ever.
In fact, that's impossible. Time flows at different rates in different places. There are places in the universe where time slows down. And if you were to visit them, you would actually get old less quickly compared to the rest of us.
This strange idea is the foundation on which Professor Millet will build his time machine.
Hi, Chandra.
Hey, how are you doing?
Fine, it's good
Glad
to
to
see
see you. Okay.
Working with Chandra Roy Choudhury, an experimental physicist who specializes in laser technology, he hopes to be able to create a machine that will use the principle of flexible time to send particles into the past.
What we're going to be looking at is trying to... Time is not the same for everyone. Each one of us travels with our own individual clock, and there are things that you can do to change the rate at which your clock is going compared to someone else's, and that allows time travel.
Although it sounds impossible, don't be deceived. This seemingly crazy notion is part of the bedrock of modern-day science. In 1905, a 26-year-old by the name of Albert Einstein showed how space, time, and also energy are linked. We know he got it right because his theory led directly to the atomic bomb. This is the very same theory that should allow real, practical time travel. And it's all to do with the speed of light.
Now, let me tell you a bit about light. Light travels very, very fast, at about 670 million miles per hour. If a particle of light were to circle the Earth, it would do so nearly 10 times in just 1 second.
Einstein's big idea was that the amazing speed of light holds the key to everything, from the untold power of the atom to the possibility of time travel. To follow in the footsteps of his genius, imagine the great scientist in a rocket ship floating in deep space. The ship has powerful headlamps, and if Albert switches them on, the light from the lamps races away from him at, of course, the speed of light, 670 million miles an hour. Now imagine that Albert has a twin brother, Bertrand, who also has a spaceship. If Bertrand flies away from Albert at very high speed, let's say half the speed of light, how fast would Bertrand see the light from Albert's headlamps if it overtakes him? You'd think he would see it pass by more slowly because, after all, he's flying along in the same direction. But you'd be wrong. The theory says he would see it pass at the full speed of light. Bertrand's own speed through space makes absolutely no difference.
This prediction of Einstein that the speed of light is the same for everyone is one of the strangest in physics. But it's true. It's been shown by hundreds of experiments. The speed of light is going to be the same, no matter how fast you're moving towards it or away from it.
Even if Bertrand turns around, he would still see the light pass him at the same speed. So what's going on? Welcome to the realm of time travel. Because if both brothers see the same speed, then something else must be changing. And that something is time.
Something has to give, and the things that have to give are space and time. It turns out that if an object is moving fast enough through space, it can alter its passage through time.
This is the famous theory of relativity, and it means there's no one true time. Time is flexible. The rate at which it passes depends on how fast you're going. The effect is not just theoretical, it has real, everyday implications. A satellite that orbits the Earth at 20,000 miles per hour experiences 0.02 of a second less per year than the rest of us down on Earth. The onboard computers have to be programmed to take this into account. Otherwise, the satellite's clocks would run constantly slow. If Bertrand's ship had some suitable equipment, we could see this mysterious effect for ourselves. This device is a light clock, two mirrors that face each other with a particle of light or photon bouncing between them. Each bounce is one tick of the clock, and in the right hands, such a clock shows directly how time is changed by speed.
These ticks would normally occur millions of times per second, but we have slowed it down to show how this clock works and how the motion of it will affect the rate of ticking. You'll notice that the clock is ticking more slowly as I move it. Why is that? Well, the photon is making a zigzag path to reach one mirror and then the other. That's a longer path that the photon has to take. And that means that it takes more time to make that path. So the clock is slowing down.
This is where physics and science fiction collide. Time for the moving clock runs slow, although if you travel with it like Bertrand, you are not aware of the change, because everything happening on board, including the beating of your heart and the functioning of your brain, would slow down by the same amount. The faster Bertrand travels, the further the photon has to go between ticks, and the slower time passes for him. What might be an hour for Bertrand could be 100 years for the rest of us. He would, in effect, be traveling 100 years into the future.
Miss?
Yes?
What about travel to the past?
Well, for a long time that was generally considered to be impossible. But then along came Professor Mallet.
While jumping to the future is fairly easy, getting to the past is a different kettle of fish. And it's not just a question of physics. There are other reasons why such two-way time travel might not be possible, or even desirable. At stake is nothing less than what it means to be a human being. On the face of it, traveling to the past is preposterous. Bob Gale, who co-wrote Back to the Future, the most successful time travel movie ever made, is well aware of the problems.
If time travel were possible, then theoretically I could go back and visit my grandfather when he was a boy. Well, let's say I accidentally kill him. Then he doesn't grow up to get married and have my father. I don't get born. So the question is, if I don't get born, who was it that went back in time and accidentally killed my grandfather? It didn't happen, but it did happen, which is called a paradox.
No matter what Ron Mallet thinks is possible within the laws of physics, it's long been thought that time travel must be impossible because of the paradoxes it would cause. Suppose that Simon Wells, the great-grandson of H.G. Wells, becomes fascinated by the idea of time travel after reading his ancestor's book and decides to travel back in time to 1894, just as H.G. Wells is trying to come up with the idea for his new novel. Let's say Simon tries to kill his great-grandfather to test the paradox.
If you think about it, it must be impossible for me to go back and kill my great-grandfather because we all know it didn't happen. He lived to a ripe old age, he wrote hundreds of books, and I was born. So, in the world that we live in, I can't change the past, even if I could travel in time.
Something must go wrong, For example, the gun misfires. For we know, as a matter of fact, that the murder attempt failed. So does that mean that time travel must be impossible? Well, not necessarily. For as long as Simon Wells fails to kill H.G., there is no inconsistency and no paradox. There is nothing to stop a time traveler taking part in history, as long as the results of those actions agree with what we know to have happened. Let's suppose Simon Wells is caught by the police and is thrown in prison for attempted murder. His perplexed great-grandfather comes to the jail to find out who it was that wanted to kill him. Simon tells him the whole story, about how he reads the as-yet unwritten book and travels back in time in an attempt to disprove the paradox. Of course, all is forgiven and Simon is let out of prison. But the intriguing possibility is that Simon Wells could, without paradox, have been the original inspiration for the book of the time machine, the book that started the whole thing off in the first place. He could, in effect, have played a role in the past. This principle means that even today we could see the results of time travel that has yet to be invented. Consider Leonardo da Vinci, the famous 15th century artist. Hundreds of years ago, he drew detailed plans for machines that are suspiciously ahead of their time. Could a time traveler have whispered in Leonardo's ear?
Even if that happened, or is yet to happen, say a time traveler in 500 years goes back and meets Leonardo da Vinci, we're already seeing the proof of it today. It's in museums all around the world.
So while it may be possible to contribute to history, to have helped it to happen, what does not seem possible is to go back and change the past, a restriction that has dire consequences for all of us.
If Ron Millett manages to build a time machine, the implications are so far-reaching, it's almost inconceivable. Take the great-grandfather paradox. I can't kill my great-grandfather, even if I intend to. So whatever my intentions are, things will happen to stop me achieving them. Therefore, perhaps, I really have no free will and everything is predestined.
A time traveler could go into the future and then come back knowing exactly what the future holds for each and every one of us. From birth to death, our lives would then be predestined, just as certain as history. We would have lost the concept of responsibility for our actions, with potentially appalling consequences for society. Thankfully, some believe that science itself offers a way out of this unpleasant prospect.
Free will is pretty fundamental to our philosophical conception of ourselves as people. But it turns out that free will and time travel are not inconsistent with each other. But to understand why, we have to investigate some pretty strange features of reality.
Influential physicist and writer Professor David Deutsch is the world's leading proponent of something called parallel universe theory.
The theory is that in addition to the universe we see around us, there are vast numbers of other parallel universes. Some of them are very like our own, differing perhaps only in the position of one atom. And others are very different. For instance, there are universes in which I'm sitting at home watching TV now, and you're being interviewed about parallel universes.
This bizarre idea comes from the study of subatomic particles, which, when put to work inside a computer, for example, display behavior that is nigh on absurd. Explaining why might save us from a future that is fixed.
If you look at the universe on a very small scale, you begin to see things that are very alien to our everyday experience. In everyday life, we're used to objects retaining their identity as they move along. This pen stays a pen as it moves. A subatomic particle typically might change into another particle or into two other particles, or particles might merge their identity and become one.
Imagine that our universe is like a pool table. Usually the balls follow the familiar laws of physics to the letter, laws that were laid down by Sir Isaac Newton over 300 years ago. But if the game were shrunk down to the subatomic scale, strange things would start to happen.
Sometimes a subatomic particle can be travelling along and then change course for no reason that we can observe. Or, if this was the subatomic world, we could put an object on the table and it could ooze right through and fall to the floor. And that's just the tip of the iceberg.
This is the strange world of quantum mechanics, and physicists still argue about what exactly is going on. David Deutsch's answer is almost as strange as the problem.
What's really happening is that the universe we see is only part of the physical reality. There are parallel universes, and each particle in our universe has counterparts in many of the parallel universes, and under some conditions these counterparts affect the particle that we can see. The universes are interfering with each other all the time.
This behavior can be explained by the particles hitting other, hidden particles, ones that belong to hidden universes, in which a different version of events is played out. These parallel universes would allow a time traveler to do whatever she or he wanted.
Suppose time travel is possible. Then you can use quantum theory to work out what would happen if you went into a time machine and travelled back into the past. The answer is that you would come into the past of another universe. And that's really why there's no problem with free will, because in the universe in which you emerge, you're free to do whatever you like, and nothing you do there will affect the universe that you came from.
Imagine a ball gets potted, travels back in time and heads for the pack, threatening its own history in a pool ball version of the grandfather paradox. If there is only one universe, something must prevent it interfering, because we already know that it didn't hit the pack. But in a multiple universe, something else happens. As the time travel occurs, the ball moves between two different games played in two slightly different universes. In one, the ball simply disappears forever, never to be seen again. And in the other, the ball appears from nowhere and disturbs the pack. Because this is not the universe it came from, there is no need for it to fulfill any particular destiny, and neither universe contains a paradox. In fact, the theory implies there is an infinite number of these parallel universes, and that time travel would simply involve skipping from universe to universe to universe. A working time machine would in effect test this extraordinary idea, and if it's correct, then not only does free will exist, the nature of reality itself is very strange indeed.
As far as I'm concerned, the paradoxes that people talk about are only going to be resolved after we build the first time machine. Then we will know whether or not free will enters into it, whether there's multiple universes, or whether the universe is determined. That's going to have to be understood experimentally.
Building a real-time machine will not be easy, but if Millett is right, then the biggest revolution mankind has ever seen will be upon us, and sooner than you might think.
Generate the 1.21 gigawatts of electricity. 1.21 gigawatts! 1.21 gigawatts! Great Scott!
What the hell is a gigawatt?
Although Back to the Future was right about it being difficult, The very fact that Ron Millett can consider such a thing a practical way to send subatomic particles or information into the past shows just how advanced our understanding of space and time really is. Nevertheless, it's only in the last few years that a serious scientist could propose such an outlandish idea.
20 years ago, it would have been close to professional suicide, but because of the fact that there's an enormous amount of articles, serious research articles in the professional journals about time travel and time machines, it's no longer considered to be part of the backwater. It's considered to be at the forefront of research today. So I'm at the front line rather than being ready to be institutionalized.
Although Einstein correctly worked out that traveling very fast sends you into the future, a further development of the theory should allow travel into the past. And even if it's only the odd particle or two, that would be a massive advance.
If Ron Millett's experiments turn out as he hopes, then it would immediately put an end to the controversy about whether time travel would ever be practicable. Because although in his machine we're going back in time really only with information or a couple of particles, nevertheless the principle of the thing is what is at stake, and that is what would have been shown to be possible. So although even in that most optimistic case, we shouldn't be expecting practicable time machines to be in the shops anytime soon, we can be confident that one day in the distant future they will be.
So how do you get from being able to leap into the future to being able to tunnel into the past? This is the core of the professor's quest, the journey that started with the death of his father many years ago. The plan is to use intensely powerful rings of laser light to twist time into a loop, an effect expressly predicted by the theories of Albert Einstein.
With a circulating beam of light, you'll create a rotating region of space, as though you were stirring at a cup of coffee. Also, in addition to twisting space, in Einstein's theory, space and time are linked. So you cause a twisting of time as well. So if we think of time, our timeline, as being a line from the past to the present to the future, if I can close that line into a loop, I can go from the past to the present to the future, but we're on a loop, so I can go from the future back into the past. It won't be simple, okay? Real world experiments aren't, but it will be able to be done.
This is the basic form the machine would take, a stack of lasers creating layers of circulating light, around which the predicted loops in time should occur. Explaining how this machine would work is something of a challenge, and in the future, in a museum that charts the history of time travel, perhaps the best way will be to start with some suitably ancient science fiction.
In the old movies, people often suggested one particular way to get to the past. All you have to do is exceed the speed of light. There was this guy called Superman. Superman flew around the Earth at such a speed that he arrived before he left. And all this to save his girlfriend's life. Now, this may be impossible, but as often happens, fiction contains a grain of truth. And if somehow you could travel faster than light, you would travel to the past. And that's the key to Professor Mallet's marvelous idea.
With Albert and Bertrand's help, it's possible to see exactly how Superman saved the day. This time, they each have a light clock to show how time is being altered. And just to show the principle, Bertrand is going to be like Superman and orbit the Earth as fast as he likes. Flying along with Bertrand, we zoom past the stationary Albert once each lap, and here, relativity comes into play. Seen from this moving point of view, it's now the photon in Albert's clock that has to take a longer path to get from one mirror to the other. So even though Albert's not moving, for us, Albert's clock begins to run slow. The faster we fly, the slower Albert's clock ticks. If somehow we could break the speed of light, the clock would not only slow down, it would stop and then actually begin to run backwards. Just as predicted, we would now be traveling into the past. But the makers of Superman didn't get everything right.
You can't go back in time by exceeding the speed of light, because there's a law of physics preventing you from even reaching the speed of light. But that doesn't mean that you can't go back into the past. There's another way.
In building a time machine, this is the ultimate challenge, to discover a way to cheat. Somehow, you have to be like Superman and exceed the speed of light, but without having to break the laws of physics. Luckily, science has known for some time about naturally occurring objects that could be used to produce just the desired effect. What you need is a rotating black hole.
A black hole is a collapsed star which is so massive and condensed that at its core not even light can escape. If the black hole is spinning, then it has a very interesting effect on the space and time around it. It drags them around with it. And that means that one can evade the rule about not exceeding the speed of light.
A black hole is so dense that a single teaspoonful would weigh much more than the entire Earth. And its gravity is so strong that even empty space has to succumb. It gets dragged around and around like water in a whirlpool. Here, on the edge of oblivion, physics is pushed to its absolute limit. Just the conditions needed to travel to the past.
One can travel in towards the black hole and into the region where space and time are being dragged round with it. Travel round with the black hole for a while and then emerge at a time earlier than when one went in.
This natural time machine occurs only because the black hole has the power to move empty space. The phenomenon is called frame dragging, and it's one of Einstein's lesser-known ideas, although a simple cup of coffee can show the principle.
Imagine that space is like the coffee inside this cup. As I stir the coffee, it swirls around due to the motion of the spoon. And suppose that I drop an object like this coffee bean inside the cup. What's happening is that it's not moving through the coffee, but rather it's the coffee that's moving the bean around.
This rotating space supplies the boost that's needed to allow an object to break the light speed barrier without violating the laws of physics.
Within that rotating region of space, you can travel speeds up to the speed of light. But for someone that's standing outside, it would appear as though you're traveling faster than the speed of light. And for them, you will disappear from sight as you're traveling back into the past.
Of course, there is a problem with this kind of time machine, for black holes are not exactly readily available. However, this is where Ron had a stroke of inspiration. He realized that hidden in Einstein's theory all along, there was something that could be even better at twisting space: light itself.
It turns out that light is much more effective at twisting space and time. And so my idea is to use a circulating light beam to twist space and close time into a loop. The key technical challenge is trying to get enough laser power to cause this twisting of space and time. That's going to be the key challenge. And we're looking at several different possibilities to overcome that challenge.
Modern laser technology is extremely advanced. lasers exist which can create conditions as hot as the center of the sun. An array of such devices could be made to fire simultaneously, producing not just a tiny ring, but a cylinder of light with enough power to twist space. An elementary particle, fired on a corkscrew-shaped path down into this tunnel, would wind its way into the past. Seen from outside, this experiment would have some pretty bizarre consequences.
I expect that particles might just simply appear out of nowhere, even though I didn't put anything into the machine. And those would be particles that would be from experiments that I perform next week or in a year from now, in which I'm sending particles back to my time, so that what I'm seeing are particles that I put into the time machine tomorrow or next year.
But there is one inescapable drawback to this machine. No matter how powerful, Ron could never use it to see or even communicate with his dead father.
This is a real time machine, and that means that when you turn it on today and you leave it on, it will only act during the time that you have it on. So if I turn it on today and I leave it on for 100 years, then I can travel from 100 years from now up to today, but I cannot travel before the machine was turned on. For me, the solace that I get from that is the fact that I will have achieved this goal, and was inspired by my father. And I think that if he, had lived, he would have been very proud of what I had been able to accomplish. So that gives me solace, that I will have accomplished an understanding of time and created a time machine. And I will be able to live with that.
So while we might like to think that a time machine would open up the past, that's not strictly true. It's only in the future that time travel to the past is possible, and then only as far back as the moment the first time machine was activated. But of course, this begs the question, what happens when you first switch on the machine?
It's conceivable that when I turn the machine on, I start getting messages from the future, from people who are trying to communicate with me. That would be a possibility. That would be weird, but it's definitely would be a possibility.
The project to build the machine has only just begun, but it is an endeavor with consequences that are hard to overestimate. If all goes to plan, it could be stable enough to keep twisting time for a century or more, becoming, in effect, a phone line to the future. Anyone with access to the machine could send any kind of information back to that first fateful energizing of the device.
Now this, the very first time machine, has been running ever since Professor Mallet first turned it on, over 100 years ago. He's probably too busy to answer it. Who wants to ask him a question?